Hello, everyone, and welcome to this OPTICA Technical Group webinar, Thermal Photonics with Polaritonic Materials for Energy Applications. My name is Hannah Walter-Pylon. I'm excited to welcome you to today's webinar, which is being hosted by our Optics for Energy Technical Group. The group has invited Georgia Papadakis from ICFO to speak to us today, and we'll begin our presentation in just a moment. While we wait for everyone to join us here in Zoom, I did want to take a moment and tell you a bit about OPTICA's technical groups. OPTICA's technical groups have been hosting weekly webinars for many years now. Our group's volunteer leaders organize and host these webinars to help bring you the latest in-depth information related to your specific research interests. In addition to these webinars, we host a wide range of virtual and in-person activities to help you connect with your fellow OPTICA members. I hope you'll take a moment and visit us at optica.org/technical groups to learn more about the 50 different technical groups we offer, find out about our upcoming activities, or access our library of over 250 on-demand webinars. So now a few housekeeping notes before we start with the presentation. We'll be addressing all of your questions for our presenter at the end of the talk today. We encourage you to submit questions throughout the presentation though, and you can do that by clicking on the Q&A button at the bottom of your Zoom window. You'll also see questions from your fellow attendees in there, and if there's a question you really want to hear the answer to, hit the thumbs up button beneath it to let our moderator know. We will be sending you a copy of this recording within 48 hours of the broadcast by email. And then when you disconnect today, we hope you will take a moment and provide us with your feedback via the survey. Now, with that, I'm going to turn the floor over to Georgios, who is a committee member for our Optics for Energy Technical Group. He's going to tell you a bit more about the technical group, and we'll introduce you to Georgia. Georgios?
Hello, thank you, Hannah, for the nice introduction. Today's talk and webinar is called Thermal Photonics with Polaritonic Materials for Energy Application, and is presented by Professor Georgia Papadakis from ICFO, Spain. I will tell you a few things about the technical group, Optics for Energy, which consists of an executive committee with, I am the webinar chair, with Nikhil Gupta, the chair, and Pietro Parda, the vice chair, and as well as social media officer Amit Kumar Garg and Susanna Ton as an advisor and past chair. We can move to the next slide and hear about a few things about the technical group Optics for Energy, which focuses on the conversion of light energy into other forms of energy, including solar conversion via photovoltaics and photothermal processes. All the aspects of the use of optics in the field of energy are considered by our group. There are over 1,800 total members, out of which over 200 are primary members. The mission of the group is to connect the group to the more than 500 primary members of the community through technical events, webinars, networking events, and social media. Past activities include networking events in OPTICA Advanced Photonic Congresses, group poster sessions at CLIO conferences, and events and webinars at Advanced Photonic Congresses in several places, all of which can be are related to the field and are available online. We can move to the next slide. And we welcome you to connect with the group, either join the online community and share your ideas for technical group events, or even let us know if you're interested in presenting your research. This can be done via several ways, either the technical group website, the LinkedIn and Facebook groups, or just email us at tgactivities@optica.org. And without further ado, I will introduce today's speaker, Professor Georgia Papadakis from ICFO, the Institute of Photonic Sciences in Spain. Georgia conducted her BS and MS studies in electrical and computer engineering at the National Technical University of Athens in Greece. In 2011, she moved to CERN in Switzerland, where she worked on the electromagnetic design for practical accelerators. In 2012, she moved to the California Institute of Technology in USA, where she conducted her doctoral studies in photonic metamaterials. In 2018, she moved to Stanford University for her postdoctoral studies in the control of thermal radiation. Since 2022, she is a tenure-track professor and group leader at ICFO in Spain. Georgia's research pertains to radiative heat engines and photonic design for tailoring thermal emission processes, with applications in sensing, spectroscopy, and thermal photovoltaics. Georgia has been an NSF Graduate Research Fellow, a Tomcat Postdoctoral Fellow at Stanford, a Princeton Pathways to the Academy Fellow, a La Caija Postdoctoral Fellow, and has also received the Marie Curie Postdoctoral Fellowship, among others. And with that, I leave to Georgia. The floor is yours.
Thank you, Yorgos. Thank you for the kind invitation. I'm really excited to be back into the world of technical groups. Can you just tell me if you can see my screen correctly or if I should swap displays?
We can see it correctly.
Okay, perfect. Thank you. So the title of my talk is Thermal Photonics with Polaritonic Materials for Energy Applications. What we do in my group is we work on thermal photonics, which means that we look into the infrared properties of emerging materials. We do spectroscopy and characterization. We also do a lot of theory, and we think about concepts in radiative heat transfer in the far field and near field. And our main objective is renewable energy applications, one of them being thermal photovoltaics, as I will explain as we go forward. The work I will present is not mine, it's the work of my group. These are the people who actually conducted the work. Some of them have moved on to new positions. Maxime is in CNRS, Michela is an editor in Nature, handling all papers in photonics, and Gloria is at EPFL. So to start with the introduction, since this is an energy technical group, I thought this may be familiar, but I wanted to give an introduction. So this is a histogram here with the energy consumed per decade in recent decades. And the obvious conclusion is that we really need to be able to produce more power density, more electrical power density. And if you look here, what this diagram shows is that more than 60% of this energy that we produce is actually wasted back into the environment in terms of in the form of waste heat. And there's a fundamental problem with that, and that has to do with this histogram here, where you can see the temperatures of this waste heat. So most of the waste heat that we reject back into the environment lies at very low temperatures. Now, if you go back into your thermodynamics books, you'll see that the ultimate efficiency at which we can recycle heat into useful work, and electricity in particular, has an upper bound, which is the Carnot limit, which is 1 minus T cold over T hot. T cold is the temperature of the cold reservoir. So for example, in a solar cell, this would be the temperature of the cell, and T hot is the temperature of the hot reservoir out of which I extract heat. So when T hot is low, as it is here for the waste heat temperatures that I'm showing here, I am fundamentally bound to operate at low efficiencies. And this, of course, shows that we really need to find ways to operate at the thermodynamic limit to make any useful power out of waste heat. And what I hope to convince you in this seminar is that you can do this with thermal photonics. So what is thermal photonics? Thermal photonics is basically the idea of using photons in vacuum instead of phonons as a source of heat. And using thermal photons, you can extract heat out of hot objects, which is simply cooling. You can extract heat out of cold objects, which is refrigeration. And you can also generate electricity. This is the main concept of a thermal photovoltaic device. So you have a hot emitter. This emitter emits thermal photons that are now received by a PV cell and generate electricity. Now, if you ask me to give you a summary of what has happened in thermal photonics in the last 2 decades, this is a very non-exhaustive slide, but these are important papers in my opinion. So in 2002, there was this very important paper by Jean-Jacques Raffet that showed that if I take a slab of silicon carbide and I make a grating out of it, because of these surface phonon polaritons that I will explain in a second that propagate in silicon carbide, I can now diffract them in different diffraction orders, and I can create thermal emission that is very directional. This is unconventional because by default, thermal emission is unidirectional. It's not coherent. So this was a breakthrough paper back in 2002. In 2014, we had this very important papers that I assume everyone in the audience knows about. This is about radiative cooling. So what my advisor at Stanford actually showed is that if you can engineer the thermal emissivity of a material to be maximum in the atmospheric transparency window, which is in the range of between 8 and 13 microns, you can actually extract heat out of objects that are directly illuminated by sunlight. And this is not just an academic topic, this is an actual industry that has been developed. And very recently, there has been this very important paper that shows that thermal photovoltaic devices can actually go beyond the Shockley-Queisser limit of solar cells. So what this shows here, and these are some important numbers, is that if I take a simple solar cell, the ultimate efficiency that it can reach is 31% of the Carnot limit for these respective temperatures that I mentioned before. If I place a thermal emitter in between the sun and the PV, in this case, I have a solar TPV, just by being able to control the thermal emissivity of these in-between layers, I can go to far higher efficiencies. Now, all of what I just described boils down to working and engineering the thermal emissivity of materials. So this equation here shows you that the thermal, the density, the energy density of emitted photons out of a hot body is simply the integration over all wave numbers of the thermal emissivity of the material times the energy of the photon, h bar omega, times the photon occupation number, which is this fraction here. So now if I go and integrate over all available wave numbers from 0 to omega over c, I will get the photon energy density. And there are many applications for which I want the thermal emissivity to be extremely narrowband, like here. This is, for example, the case in lighting applications. If I want to make a very bright source, if I want to actually make a very absorbing PV, or in spectroscopy or sensing. And there are many applications where I want a broadband thermal emissivity, for example, for a radiative cooling. There are applications where I want the thermal emissivity to be a function of temperature, to be very directional, to be chiral, and this is what I'm going to be discussing in this presentation. But before we go into actually engineering the thermal emissivity, let's look at what is the palette of materials that we have available in this spectral range. So here's the blackbody spectrum of the sun at a very high temperature of 6,000 Kelvin. But now as I decrease the temperature, the peak of the blackbody spectrum actually redshifts a lot. So for terrestrial temperatures in the range of 300 Kelvin, we're actually in these very low photon energies. And in fact, we're in the mid-IR. So in the mid-IR, if I look at the dielectric function, so this epsilon here is not emissivity, it's actually the dielectric permittivity of dielectric materials, you'll see that they have these very narrow phonon resonances. So when the dielectric function actually goes negative, this is what we call the Reststrahlen band. And it's a very interesting regime because when the permittivity is negative, we have these surface polaritons that propagate in the material. And these phonon polaritons, in contrast to plasmon polaritons, have this very narrow bandwidth, which makes them very low loss. Now, there are many important papers about this topic. Here, I just put 2 review papers, one for bulk materials, conventional dielectrics, and one for van der Waals materials. So in this talk, I'm going to be talking about different topics. All of them can be found in these papers here. So let's start with some fundamental limits in order to understand what we can really do by harnessing light for energy. So here on the top, I put a discussion that is probably already known to the audience. So if I have a solar PV, the Shockley-Queisser limit, so the limit for a PV that is conventional, it doesn't have an exotic response or some non-reciprocal response, for example, is 33%. Now, this means that 33% of the incoming light can be extracted and generate electricity. And instead of showing exact numbers of efficiency, I normalize all the efficiencies to the Carnot limit. So I take the temperature of the sun, which is 6,000 Kelvin. I take the temperature of the cell, which is 300 Kelvin. So 33.7% actually corresponds to 34% of the ultimate Carnot thermodynamic limit for these temperatures. Now, as I already said, if I take a solar TPV and I put a thermal emitter in between, and I make the bandwidth of this thermal emitter, the emission coming out of this thermal emitter that is heated by the sun, very narrow band, you'll actually see that I get a much higher thermodynamic efficiency. And if I work with other type of thermal emitters that are directly heated by some external source, you can get much higher numbers. And there's many interesting topics and physics that you can harness in order to actually get this very high efficiency. Now, here's some experimental results that come from recent years. So this is where the Shockley-Queisser limit is. And you can see here that many experimental papers have already surpassed the Shockley-Queisser limit in TPVs, where the efficiency is defined by the electrical power density that is extracted out of the cell divided by the photonic heat exchange between the emitter and the cell. Now, the absolute power density is, of course, current times voltage. And as you can see here, in recent experiments, we're almost reaching 10% of the blackbody limit. So I normalized the power density to the blackbody limit, sigma t to the 4th, and we get roughly 10% of that. But are these fundamental limits, or how close or how far are they from fundamental limits? So if I plot the power density that I just described and the efficiency, and all the experiments that I'm showing in this slide here would lie in this very low, small corner of the diagram, whereas these curves demonstrate the fundamental limits. These fundamental limits pertain to the reciprocal case and to the non-reciprocal case. So this orange curve basically demonstrates the multicolor limit. So if I take infinite PVs and I put them one next to the other and I separate the spectrum into infinitesimal spectral ranges and each cell converts a little bit of the spectrum, I get this trade-off between power density and efficiency. And as I said, this is just to show that there's really infinite room for improvement in TPV research. One way to actually reach the reciprocal limit, the multicolor limit, is what we discussed in this paper here. So what we thought is something that has been already considered in the case of solar PVs. So solar PVs have been investigated in terms of hot carriers, and here we do the same for solar PVs. So we thought, okay, a standard PV will be most happy if it receives energy from the sun that is very narrow band, and a TPV the same. But if I extract more photons and I actually create a very broadband spectrum, I have an emitter that emits photons from the bandgap all the way to infinity, and I can actually extract these photons before I let them thermalize, which is what this diagram shows, then I can actually reach the endo-reversible limit. So this diagram shows that if I take selective contacts and I can extract hot carriers that are generated inside a PV at temperature T, which is different than the temperature of the lattice, which is TC here, I actually get an open circuit voltage that is much higher than the open circuit voltage of a conventional PV. So if I set the temperature of the lattice T equal to the temperature of the cell, which is TC, this term goes to 0, and I have the standard, I recover the standard VOC of a solar cell. Now, if I look at the diagram that I showed before, here are 3 different curves that show the power density and efficiency of a hot carrier TPV as I decrease the bandgap of the cell. So by decreasing the bandgap of the cell, I basically allow more and more photons to come into my cell, and I integrate for a larger spectral range, so I get more power density. So as you can see, for 0 bandgap, I actually recover this endo-reversible limit, which is the multicolor limit described in the previous paper that I showed you. So with a single junction ideal hot carrier TPV, I could actually reach the anti-reversible limit. Of course, this is a theoretical work, and hot carrier PVs are intensely being investigated now recently. Now let's look at this blue curve here. This blue curve corresponds to non-reciprocal PV cells and TPV cells. As you can see here, in the case of solar PVs, if I could allow non-reciprocal cells, I would get to 93% of efficiency, which is gigantic. So what do I mean by that? If I could break the Kirchhoff's law that dictates that the thermal emissivity is equal to the absorptivity of a material, I could create PV cell configurations that look like this. And in this case, a cell absorbs from one side, for example, absorbs direct sunlight, but then the emission of the cell, because everything that has a non-zero temperature emits, is directed towards another cell. And in this case, Martin Green showed here that indeed I can recover the Landsberg limit. Of course, it's far more easy to do this in transmission mode. So this is a more recent paper that shows a similar concept where by enabling non-reciprocity in materials, I can actually get the Landsberg limit. Of course, recently, there has only been one experimental demonstration of breaking Kirchhoff's law, and this is this paper here, where they achieved this by applying a magneto-optical, using a magneto-optical material, indium arsenide, in this grating form. But you can see that it would be very difficult to actually integrate a grating like this into a PV configuration like this one or this one. So here I'm showing you just very, very briefly two works that we have done in recent years where without any lithography, we demonstrate how you can break Kirchhoff's law on reciprocity in reflection mode, for example, here, and in transmission mode. And the way you can do this is basically using simple wave interference. In this case, we have what is called a Salisbury screen. So we have a material that is non-reciprocal on top, a dielectric spacer and a reflector on the backside. And here we have the non-reciprocal material sandwiched between two other materials. And you can see that in this case, one can absorb light from one side and really emit from the other towards the other. And here you can see that in transmission mode, you can do this for both linear polarizations, which is what you would need in order to actually get closer to this theoretical proposals for reaching the efficiency of 93%. Now, let's talk more about materials and about how to engineer the thermal emissivity and some experimental results. So, as I said before, the blackbody spectrum is spectrally broad, and it's spatially diffuse and unpolarized. It's omnidirectional, and there have, of course, been in recent decades many proposals and ways of how to modify the characteristics of the blackbody spectrum in order to make it narrowband, directional, etc. But these, most of the times, require significant lithography and complicated designs like the ones shown here. What we do in my group instead is we leverage the intrinsic properties of emerging materials to achieve thermal emission that is unconventional. It's chiral, it's directional, it's actively tunable. So let's start by looking on ways to control the polarization at mid-IR frequencies. So to my surprise, when I started my group, actually, I realized that a very important optical component, a phase retarder, is very difficult to find in the mid-IR range. So no commercial phase retarders exist at wavelengths above 10.6 microns. So a phase retarder would be a half wave plate or a quarter wave plate, for example. So to build a phase retarder, what you need is a material that is, of course, transparent, and also it's anisotropic, and in particular, it's birefringent. So orthogonal to the plane that light propagates, you'd want it to be anisotropic. However, if you look at this plot that I showed before, all dielectric, so transparent materials in the mid-IR have these strong absorption peaks. So you can use them, but you can never use them in a broadband way because at some point they're going to absorb heavily. And also the birefringents of most anisotropic materials is actually very weak in the mid-IR. Now, this means if you look at this equation here, where delta n is the birefringence, that I would need a very, very thick phase retarder in order to achieve half-wave plate or quarter-wave plate operation in the mid-IR. However, what we did is we looked at this emerging material that is called molybdenum trioxide. And as you can see here, where we show the permittivity along the X, Y, and Z directions, it's very different. So in the X direction, it has a resonance or a phonon around 10 microns. But in the Y direction, it's a different frequency. So this material on resonance is actually extremely anisotropic, and it has a birefringence that is roughly 8, whereas most materials have a birefringence that is on the order of 0.1. So here we did a calculation of the thickness of a half-wave plate made out of conventional materials and molybdenum trioxide. So for these conventional materials, you see that, first of all, you are in the very thick wave plate regime. So these are optically thick materials that are tens of wavelengths, if not thicker. In addition, these curves actually terminate, and when they terminate, it's when you actually have an absorption peak, so the material cannot be used anymore because it's not opaque. By contrast, here you can see in the red line, the regime of operation of molybdenum trioxide as a half-wave plate, where we actually operate at the resonance. So in fact, we operate where the material absorbs heavily, but because the birefringence of this material is gigantic, the material can be extremely thin. So even if it's lossy, it actually remains transparent. So we actually went ahead and built these devices when we characterize them in transmission and in reflection mode. And you can see here, for example, that coming with parallel and orthogonal polarization, which refers to just orthogonal or parallel to one of the axes of the material, you can see that within the Reststrahlen band that I showed before, the polarization totally flips, which is exactly what is the definition of a half-wave plate. You can see here that in the output, we don't have an exactly linearly polarized light. We have actually elliptical polarization. And this is simply because to get perfect operation, you need the thickness of the material to be exactly what you calculated. But the problem with these materials is that you exfoliate to get them. So it's very difficult to get the exact thickness right. Our next question was, okay, this was interesting, but now how can we use it in order to actually engineer thermal emission? And our goal was to actually create chiral light in the mid-IR. So usually, in order to engineer chirality, one would need to lithographically pattern structures that look like this. So they look chiral to the eye. So they break a rotational symmetry and mirror symmetry. And these are, of course, very complex devices to build. So what we did instead is we considered just 2 flakes of molybdenum trioxide, one on top of the other, that are twisted with respect to each other. And if you look at this configuration, it breaks rotational symmetry and it breaks mirror symmetry. So it is actually intrinsically chiral. So here's a simple calculation where by changing the angle, the twist angle between the 2 flakes, you can see that, again, within the frequencies where you have this very strong absorption peak and these Reststrahlen bands, the circular dichroism of this device actually goes up to 1, which is very unconventional. So the next thing we did is we actually built this. So we started with a single flake, and then we exfoliated a second flake and carefully placed it on top of the first flake. And here's an AFM picture of that. So these are not very thin flakes. We don't need thin flakes in the mid-IR. And once we had our device, then we had to characterize it. And of course, this took a very long time because, as I said in the previous part of the talk, phase retarders don't exist in the mid-IR. So we needed a quarter wave plate in order to generate circularly polarized light in order to characterize chirality. But we didn't have that because it's simply very difficult to purchase commercially. So first we tried to do it with a photoelastic modulator in this very complicated experiment that didn't work. And in the end, we did it with with our own FTIR by modifying things a little bit. So the most important thing to remember here is that in order to do thermal emission with an FTIR, you basically need to replace the blackbody source of the FTIR with your material sitting on top of a heating stage. So now the source is the material itself, is the sample. These measurements are very difficult because, as you can see, these flakes are actually only 40 micrometers wide. So the thermal emission that comes out of them is very small compared to the thermal emission that comes out of every other component that is in the lab. Nonetheless, we have been able to actually very accurately measure the thermal emissivity, which is shown in the yellow line here. And this is actually the ellipticity of the beam that we get. So you can see that it's not perfectly circular, it's actually elliptical. Nonetheless, this is proof, this is an experimental proof of generation of circularly polarized light that has a specific handedness, thermal generation of such light. And the blue curve is simply the circular dichroism that goes up to 0.2 because, of course, we don't have these very large devices to get all the way to the theoretically expected result. Something else that is really interesting to us for application purposes specifically is directionality. So it's really important, yet really difficult to confine thermally generated light into a very narrow spatial regime. However, it's very important. And here I'm only listing 3 reasons why it's very important. One of them being to build cheap thermal sources. So in the mid-IR, the only light source we have in the form of a laser is a QCL laser, which is very expensive. We don't have LEDs that operate in the IR, and the reason for that is that semiconductors have these non-radiative recombination that becomes very, very large and parasitic at low photon energy, so in the mid-IR range. Another important reason is that we want to be able to actually control the directionality of radiative cooling, because now that radiative cooling is an actual technology, people don't place coolers just in horizontal structures and on top of buildings, but they actually place them on the side of buildings and in any other configuration that you can think of. And the atmosphere has a angle-dependent transmission coefficient. So taking that into account, you'd really need to get directionality in thermal emission. Another very important reason is that roughly 30% of the losses in the VOC, in the open circuit voltage of solar cells, comes from the fact that the light emitted out of a solar cell is wasted in many directions that are unwanted. So people have been building these very complex configurations for solving this problem. And it boils down to making thermal emission very, very directional. Now, how can you do this? Of course, the simplest way to do it is to mimic what Jean-Jacques Raffet did in 2002 in this Nature paper, where, as I said before, he built these nice gratings, and he basically building these gratings allows that the propagated surface phonon polaritons in silicon carbide, one of the best materials for mid-IR photonics, diffract, and they diffract in different diffraction orders that you can see here with these very narrow lobes. However, this approach is polarization dependent. And the reason why it's polarization dependent is because surface phonon polaritons can only be generated for transverse magnetic polarization. Also, it requires high resolution lithography. And it requires a material that has a negative permittivity. By contrast, what we did is we looked at a very old concept, and that is the concept of a Salisbury screen. So a Salisbury screen is a device that has an emissive thin layer on top, a dielectric spacer, and on the backside, it has a conductor, which is basically there just to reflect all the photons. So this works based on constructive interference. However, in its standard version, it creates spatially diffuse light. On the positive side, it is a planar structure that requires no lithography. And it works for both polarizations. So what we did in this paper here is we went back and revisited the physics of a Salisbury screen. And what we saw is that if we relax the standard conditions for a Salisbury screen that are described by this equation here that matches the phases of the incoming light with the light that comes out of interference in this dielectric spacer here, is that if we make the emitter a little bit thicker than this limit of ultra-thin emitter shown here, then you can actually generate very directional thermal beams. So the standard Salisbury screen works in absorption, of course, and is used for microwave frequencies. However, here we use a Salisbury screen in emission mode. So this is a calculation of a Salisbury screen with a thick emitter. And as you can see, here, it works for both linear polarizations, and it gives the same emission lobes as what Grafette's grating would generate, except it requires no lithography, and it works for both linear polarizations. And the key to actually building something like this in practice is not so much that you build a thick emitter, but you choose a material that has a very high index, because what really matters is the optical thickness. So this is exactly what we did. So we chose to work with an emitter that is silicon carbide, and we did this in order to be able to compare apples to apples, to be able to compare with Jean-Jacques' experiment from 2002. So we built the Salisbury screen, which was not easy. And the reason why it was not easy is because you have to build a dielectric spacer. And in the mid-IR, a dielectric spacer in the order of the wavelength means that we have to have a dielectric layer that is on the order of 10 microns or so. And that's very difficult to get because of buckling and Iceland formation. So after struggling a lot with this, we actually decided to take a silicon wafer and etch a wedge out of it. And then we purchased commercial membranes from Norcada that are freestanding, and we placed them on top of the air gap. So this is how our devices look, and they are in the order of millimeters. So these are gigantic thermal emitters. And as you can see here, this is an AFM figure of the wedge that is exactly 8 microns thick. So the first experiment we do is simply we put the device inside the microscope, and we do absorptivity measurements. And what these really are reflectivity measurements. So we really just measure reflectance, and we take -1 minus R, which is the absorption. And then we also put the material on top of the heating stage, we heat it up, and we get the emissivity, and of course they have to be equal due to Kirchhoff's law. And then we take it out of the microscope in order to do angle-dependent measurements, and here you can see the simulations and the experiments, and these all pertain to wavelengths that are close to the Restralin band of silicon carbide, where its dielectric function is very high. And you can see that for both linear polarizations, we get these emission lobes that look like an antenna, except we don't even have a grating. We have a simple planar structure. Now, what we really wanted to do in order to enter the regime of real applications is to also work with devices that are actively tunable. So in order to induce active tunability, one of the simplest ways is to work with phase change materials. So we did something very, very simple, which is we took a standard Salisbury screen, now that you know what it is. So we took an SiO2 layer on germanium and on gold. So SiO2 has an emission resonance at 10 microns. So this material is very resonant. This device is very resonant when you put on top of it a dielectric material, a transparent material in the mid-IR. So what we put on top is IST, and IST is a phase change material that has this dielectric response. So in its amorphous phase, it's actually dielectric and transparent, but in its metallic phase, it's reflective. So when I change the phase of IST, it actually becomes very reflective, and no emission or absorption is possible. Here you can see the angle dependence of this. So this is a diffuse source of IR light. And here what you can see is that we actually went ahead with a laser, and we created patterns, these chess patterns, where the material, the top material is IST, and in the one phase, it's in the amorphous phase, and the other is in the crystalline phase. So these are the actual microscope images. And then we took FTIR images, absorptivity measurements, that we averaged over a short wavelength range where the material emits from 9 to 10. And you can see here that this structure that has the same temperature across it actually looks like certain areas emit more than others. And this is simply because of the IST on top having different characteristics. You can
Georgia,
actually...
5 more minutes.
Good, great, thanks. You can actually pattern things in a very large scale, so in the centimeter scale here, and you can see that you get the same result. So you get a very bright light here, and whereas the surrounding of the sun is actually looks like it's cooler. And what I said before is that it looks diffuse, meaning that it doesn't change with the angle of incidence, which means that it's an actually very bright source. So just to give you a summary of what I discussed. So I hope I convinced you that there is tremendous potential in working on radiative heat engines and thermal photovoltaics, because we haven't even gotten close to the thermodynamic limits of what is available in with non-reciprocal and with reciprocal materials. Now, sticking to reciprocal standard materials, there's a lot of things you can do by harnessing phonon polaritons, and I showed you that you can create chip-scale directional thermal emission without any lithography, simply by taking membranes of polaritonic materials and building Salisbury screens with simple air or vacuum as the dielectric laser spacer. I showed you that molybdenum trioxide can serve as a phase retarder. So single flakes of molybdenum trioxide can serve as phase retardation schemes in the mid-IR where commercial phase retarders don't exist. Twisting these anisotropic materials with respect to one another actually creates chiral light. And phase change materials like IST are very promising for actually inducing active tunability in all these functionalities I described. So this is the funding, and thank you very much for the introduction, and thanks to my group that did all the work.
Thank you so much, Georgia. So we're going to move to the question and answer session now. If anyone here has a question, please go ahead, add it to the Q&A box. It's helpful if you add it there rather than to the chat, just so we can track the questions and mark them off as answered. And with that, I'm going to turn the floor back over to Georgios to moderate the Q&A.
Thank you. Thank you, Hannah. And thank you, Georgia, for a very interesting presentation. There is one question from you, Eon Yim, and he asks, what temperature was your thermal emission of molybdenum oxides measured? Also, could you give us some tips of how to minimize the background emission?
Yeah, whoever this person is, he knows he's probably done some painful measurements. Yes, so the temperature of molybdenum, so the temperature, the real answer is I have to ask my student, but it's lower than 120 Celsius, because for silicon carbide, we could go up to these temperatures, but molybdenum trioxide actually is very sensitive and it cannot tolerate these temperatures. So it's lower than 120 degrees. These temperatures are, these measurements, as I already said, are very sensitive. So in fact, at some point we stopped having multiple people in the room, because the people themselves, if you have many people in the room doing the experiment, we also emit, or everything emits. So one solution is to purge. In our cases, we didn't actually purge. So these are these measurements are without any purging, but basically you have to eliminate any gases. You have to keep everything around very cool in order to minimize the temperature, to minimize the background thermal emission. And what we do in order to minimize the noise is we take infinite measurements. So I think this was a repetition of something like 24 measurements for every different configuration of the polarizer and the wave plate in order to get these curves here. So it's not an easy task. It's much easier when you have very large samples like here. But if you have small samples, it's a serious effort.
Thank you, Georgia. We have another question from Christos Argyropoulos. He liked the talk, excellent talk. Any ideas how we can make the directional thermal emission more broadband either with silicon carbide or another material or technique. This will be very interesting to manipulate thermal radiation.
Yeah, that's true. So yeah, as I said here, hi Christos, for radiative cooling, for example, you need a broadband directional thermal emission. If you look at this paper here, where we derive the analytics of this, the key requirement is actually a high permittivity. So the reason why this is narrowband in our case is not because the physics don't work otherwise. It's just because silicon carbide has a very high refractive index for a very narrow band frequency range. If you could find a material that has a very high refractive index for a broadband, or at least more broadband spectral range, then it would work. So basically, it's restricted by the regime where the dielectric index of the emitting material is high. So I unfortunately, I think that all these polar materials are quite have a very small line width, so they are very narrow band. I cannot think of ways, but there's a nice paper in Science by Ashwath Raman where, in a very different approach, he actually gets directional emission for broadband light.
Right. We don't have another question at the moment. While we give some more time to the audience, I have a question. I noticed it was alpha phase molybdenum oxide, right?
Yeah. I didn't say it. It's alpha phase, yes.
The question is it only the particular phase or other phases are required?
Yeah. It's only the particular phase that is anisotropic. Yes.
I guess you tried the experiments on other phases as well.
No, we did not. We did not actually. We purchased alpha molybdenum trioxide, alpha phase, and we exfoliated ourselves. So we only purchased that. Yeah.
We have another question from Stevie Cordet. He also liked the talk. Excellent talk. Could you give us a cost estimation of the suspended membrane solution?
A cost estimation, how much they costed?
Yes.
I think they're not expensive. They're like 500 euros. So yeah. This is a nice concept, I think. Yeah, these are cheap.
Okay. I don't think there are more questions from the audience, so I can move to Hannah to maybe
Actually,
close
looks
up.
like we just had one come into the chat.
Yes, I just noticed from the chat. From Silpa S. He asks for the solar PV in the design where the emitted light is directed towards from one PV to another PV. They ask, will it be possible to delete the reflected light contribution?
In these configurations here? Say the
Yes,
question.
here it is this one, yes.
Can you repeat the question so I understand?
Yes, they say for the solar PV in the design where the emitted light is directed towards from one PV to another. Another PV.
Would it be possible to minimize reflection?
To delete, yes.
Yeah. So to get to these numbers, these concepts here by Martin Green, and this is by Xianghui Fan, assume zero reflectance. So they assume that the material is only transmitting and absorbing and emitting, and only absorbing and emitting. So these are ideal calculations. Yeah, so that's what I can say. In these cases here, it's the same actually. We by using interference, you can actually, this is the concept of a Salisbury screen. This is how you you can actually get zero reflection, which is how you get unity emissivity by simple interference. I'm not sure if this is the question that was asked, or if I'm answering the right question.
I think it's now more clear that the yellow and red lights are not reflected, but emitted.
No, they're absorbed, and the red are emitted. Yes, so there's no reflection there. Yeah.
There is no other question, and I think no one is writing. So I'll move Hannah back to you to wrap up the session.
Thank you very much. Well, thank you, Georgia, for being here and presenting to the Optics for Energy Technical Group. We really appreciate it. Everyone, thank you for joining us today. We will send you the link to the recording within 48 hours. And please, if you have a moment to fill out the survey when you disconnect, we'd really appreciate your feedback. So once again, thank you all so much and have a wonderful rest of your day. Bye.
Thank you. Thank you for inviting me.